Okay, moving on here to the last part of these practice problems. So I'm repositioning here because I was made aware of a mistake in the video. So I'm trying to reshoot here quick so I can replace the one with the little rearrangement error in some of the algebra going on here in problem number 5. So looking at number 5 here, we're told normal melting point for carbon tetrachloride, or determine the normal melting point for carbon tetrachloride. And we're given the enthalpy of fusion and the entropy of fusion. So one thing to notice here, or to recognize here, is that melting is an equilibrium process, right? If something is melting, you could add a little more heat, that would push it toward liquid. If you removed a little bit of heat, that would push it towards solid. But it's a process that can go in either direction, so it's equilibrium. Well, at equilibrium, that means delta G is equal to 0. So if we start to plug into this equation for free energy, right, we can plug in 0 for free energy, we can plug in the values here for entropy and enthalpy, and we can solve for the temperature here. So if we do that, 0 for delta G, 2.67 kilojoules for delta H. The temperature here, I'll just call T, that's what we're going to solve for. And now I need to multiply by the entropy change. Well, the possibly tricky thing here, and certainly what you want to keep track of here, is free energy, entropy are in kilojoules, right? So they're kilojoules or kilojoules per mole. Entropy units, though, are joules per kmol. So this entropy value is in joules. What we're going to want to do down here is subtract after we multiply by the temperature. So what I really want to do is change this to kilojoules. So 10.86 joules per kmol. If I multiply that by 1 kilojoule per every 1,000 joules, so really dividing by 1,000 there, that's 0.01086 kilojoules per kmol. That's how I want to plug it into my equation. So 0.01086 kilojoules per kmol. And from there, now I can solve for T. So this would be 0 equals 2.67 minus T times 0.01086. Right? And all the units are the same. We made sure of that, so that will simplify things. So let's move the numerical term over here. Minus 2.67 is equal to minus T times 0.01086. Right? So I'm going to drop both those minuses, and I'm going to divide both sides by 0.00186. So that would be 2.67 divided by 0.01086. Right? I misplaced this 0 in the first version, and I divided by 0.018, which changed the answer enough to make it problematic. So that's why I'm redoing the video here. So if I do that division, 2.67 divided by 0.01086, that comes out to 245.8. Now I'm just going to round that, right? We're dealing with 3 significant figures here going back to our enthalpy value. So let's call that 246 Kelvin. Right now, 246 Kelvin, if I take 273 and subtract 246 and subtract 273, that would be minus 27 degrees Celsius, since 273 is 0. So that would be the temperature at which carbon tetrachloride would be melting, right, or freezing, depending on which direction we are going. Okay, moving on to question 6 here. The venom from stinging ants contains formic acid. We're given the equilibrium constant for that weak acid. We want to calculate the pH of a 0.25 molar solution. So with any acid, we are looking at this equilibrium. An acid is going to protonate the water in its aqueous solution to make hydronium ions, and that's going to result in formation of the conjugate base. Now in this case, this is formic acid. The conjugate base would be formate, right? But that's irrelevant to the problem, since all we're really trying to do here is solve for the concentration of hydronium ions, which we can relate to the pH. If we fill out our ice chart here, we start with 0.25 molar concentration of the acid. Of course, the initial conditions, the reaction hasn't moved at all, so there are no products. So we know as we approach equilibrium, we'll lose some of the weak acid, and we'll gain that much in the products of the reaction. So at equilibrium, 0.25 minus x, and each of the products would be x. Now, what we usually will do here with a weak acid problem is we'll go and evaluate the negative x here term and see if we can ignore it. So what we want to do here is compare the concentration of the weak acid to the equilibrium constant. So if the concentration is really low, or if the equilibrium concentration is fairly high, we may not be able to ignore that minus x because the equilibrium may shift a lot in the forward direction. Now in this case, if I take 0.25 and divide by 1.8 times 10 to the minus fourth, I get 1,388.8, and the 8s keep going. So 1,388. What we generally have said is if that ratio is greater than 1,000, it is appropriate to ignore or make the assumption that minus x can be left out of the calculation. So we're above 1,000, we'll eliminate the minus x, and we don't need the quadratic equation then, which that makes the problem a lot simpler. So the equilibrium constant here would be the products, hydronium and the conjugate base, divided by the concentration of the weak acid. Plug numbers in for those values, and we get 1.8 times 10 to the minus fourth is equal to, both of the products are x, so x squared on top. And since we eliminated the minus x, just 0.25 on the bottom. And now that, pretty straightforward to solve that for x. So I'll take 1.8 times 10 to the minus fourth, multiply through by 0.25, and then take the square root. And I'm left with x is equal to 6.708 times 10 to the minus third molar. Now, based on our ice chart, x is hydronium ion concentration. So we can use this hydronium ion concentration to calculate our pH, since pH is the negative log of the hydronium ion concentration. I think that number is still in my calculator, so I'll just take my log, and then I'll change the sign, and the pH here is 2.17, and that's our answer. So formic acid is, it's a fairly strong, weak acid. Weird a little bit how the terminology works there, but 2.17, that's enough to cause some discomfort when those ants do kind of inject that into you when they bite you. Okay, that's all for the video reviews. So good luck with your studying, and I'll see you at the final exam.